A usual EDA workflow starts with the schematics, which is then forward annotated to the PCB layout process. This tutorial focuses on the first half of the PCB layout process, marked with green on this workflow diagram. The input is the blinking LED schematics drawn in the SCH-RND Getting Started tutorial. This video focuses on the bare minimum, refinements, more advanced, more efficient editing, and the second half of the workflow will be covered in subsequent videos. PCB-RND is Unix software. It is normally started from a terminal, and the current working directory matters. Starting PCB-RND from the project's directory where the schematic sheets and board files are stored makes life easier. When started without arguments, PCB-RND creates a new empty board by loading a template. This new empty board does not have a file name. First, save the board. Since there is no name, this first save acts as a save as, asking for a file name. The file selection dialog shows the directory PCB-RND is started from. Edit the file name, keep the .rp ending and click OK to save. The main window of PCB-RND has the board editor in the centre right, the layout selector and routing style selector on the left, menus, toolbar and coordinate readout on the top and status bar on the bottom. The most important widget is the blue Help button on the top right. This pops up a built-in IRC client that joins a PCB-RND channel where you can get real-time support from other users and developers. Say hi and wait a few minutes to see if there's any response, if anyone is awake. If you ever get stuck or have questions, please don't hesitate to use this feature. The default board template comes with 4 copper layers, while this simple blinking LED board requires only 2 layers. We need to reconfigure the layer stack-up. Open the Preferences dialog. Activate the Layers tab. First we're going to remove the 2 inner copper layers. These are physical layers. The terminology for that in PCB-RND is layer group. So we are removing 2 layer groups by dragging and dropping the Del Copper Group button on them in the board cross section. We are now left with only the top and bottom copper layers, and each have 2 logical, also known as drawing, layers. For this simple board we are going to route signals on the top layer and use the bottom layer mostly for ground. Removing excess layers is done by dragging and dropping the Del Logical Layer button on the layers to remove. Now we have the right number of physical and logical layers, but their colours are too similar. Right-click over the bottom ground layer to get the Layer Context menu and select Layer Properties. In the Property Editor, select Layer Colour and pick a new bluish colour and click Apply. When finished, close the Property Editor and the Preferences dialog. Besides the layer stack-up, another important aspect is sizes. Trace thicknesses, minimum clearance, via hole size. Normally this is the best time in the workflow to set those up. For this tutorial video we are going to skip that. Defaults are good for both home etching and fabbing. Changing sizes will be covered in a subsequent video. A netlist tells PCB-RND what should be connected where, so it can help the user making the right connections. Importing a schematics is a bit more, as it also imports metadata, footprints, component values, etc. Open the File menu, Import and Import Schematics. This will bring up the Import Schematics configuration dialog. The first thing to select is the format to work from. This depends on the schematics editor used. Some of these assume the file is manually exported from the schematics editor. Others run the command to get the netlist exported. The default is SCH-RND, which will automatically run SCH-RND in the background to export the netlist. We need to specify either a project file or one or more schematic sheet files for input. The list is empty. Click on One More to create an entry. You can either enter the file name directly or use the Browse button to select it in a dialog box. Once done, click on Import to perform the actual import. This will run SCH-RND in the background to export a netlist of the schematic sheet specified, then loads this netlist and loads all footprints. Once footprints are loaded, they are called subcircuits and are placed around the drawing area after an import. If we remove a subcircuit and do an import again, no format or file name need to be filled in. PCB-RND remembers import configuration. It is saved in the board file. Since the schematics didn't change and still contains the symbol for the subcircuit we have deleted, it's added back in a new import. The netlist window is useful for verifying the imported netlist. Pressing the hotkey sequence CR optimizes the rat's nest. It compares the netlist to the current state of the board and creates a rat's nest which consists of yellow rat lines indicating missing connections. CR also prints a message to the message log indicating how many connections are still missing. The next step is to arrange our subcircuits on the board. This is done by dragging them to where you want them, which works without having to select them first. There are different strategies to find a good placement. For this video we're using a simple manual method looking at rat lines. We're simply shuffling subcircuits around until there are only a few rat lines that are crossing. First we're doing a rough approximation of the final placement, without trying to adjust things for a pretty arrangement. When a refdes text is dragged, it moves instead of the subcircuit, because the refdes text is a so-called floater that can be moved freely. This lets you move both the subcircuits and the refdes. However, during placement it is more useful to move subcircuits only. Using the hotkey sequence UU, the accidental refdes move is undone. Then in the Mode menu, the Lock Floaters option is enabled. This way, floaters never move, so it is easier to grab the subcircuit. It is a good idea to choose an appropriate, not too dense grid for placement. For this classic through-hole board, 100mm is chosen. The grid is indicated by red dots in the drawing area and is printed in the bottom status bar. Object Snap makes the crosshair jump onto non-grid aligned pins. Once grabbed and moved, these pins will land on the grid. The crosshair can be used to line pins up. Switch to the Rotate tool to rotate subcircuits. Switch back to the Arrow tool to move things. The Arrow tool can also be activated by pressing Escape or F11. After all the shuffling of subcircuits, press CR to optimise the rat's nest. This will rewire the rats to shortest, making remaining connections easier to see. Pressing CF while hovering over a copper object will highlight all the connections in green, both galvanic connection made by copper objects and logical connections made by rat lines. This can help oversee the mess. With a cap rotation and resistor swap, the rat's nest looks much simpler. Now that we have reached a reasonable placement, it's a good idea to save. On this simple board, we're going to put all subcircuits on the top side. But in case we wanted to use the bottom side, a right click over the subcircuit pops up the subcircuit context menu, where moving to the other side is a submenu. Pressing the Tab key will flip the board view, so we're now looking at the board from the bottom. Pressing Tab again flips back to the top view. It's possible to flip among the other axes or rotate the board by 180 degrees using Shift Tab or Control Tab. Right click and most editing features reach things on the other side. However, if there is an overlap between a current side and an other side object, they prefer the current side one, and the precedence can be changed by flipping to the other side. Hover the mouse cursor over a pin and the subcircuit revdes, terminal number, terminal name and network connection from the netlist are printed. We have decided earlier that the bottom side of the board will be mainly for ground, so we shouldn't route the ground network on the top side. With the terminal info pop-up, it's possible to figure out which pins are to be connected to the ground, but there is a simpler way. It is possible to remove the ground network from rat line generation. For this, open the netlist window, select the ground net and click on the rat disable button. The disabled rat generation is indicated by an asterisk in the table, and pressing CR over the board will omit all ground connections. Now we can focus on routing the rest of the top SIG layer. Click the line tool and make sure top SIG is the active layer. Click at the start point. Red wireframe shows how the trace would look while the mouse cursor moves. Grid snap ensures the line ends on a grid point, while object snap pulls the cursor into objects like pins. For placement, the 100mm grid served as well, but for routing, a 25mm grid is more practical. The second click finalises the trace, built of 2 lines. Pressing CR will optimise the rat's nest, which now finds a shorter connection to LED 2. Looking at this new rat's nest, it looks like avoiding the 45-degree lines could make connecting this net simpler. Press UU for undo a few times until the copper lines are removed. Press CF over the pin of B1 we are starting from. This highlights objects to be connected, which makes it easier to see where to route. For the sake of the example, click the Power style in the Route Style selector. This changes the pen to use a thicker trace. Draw a vertical line using 2 clicks, then press Escape so the line is not continued. The line tool is still activated, so start drawing a horizontal line across the LEDs. Using the same click, click, escape trick, it's quick to draw this network from disjointed line segments. Now switch back to the signal route style to get thin traces. Drawing the vertical traces is easy enough. Don't forget to save from time to time. By default, a dog leg of 2 lines are drawn. First axis aligned, second 45 degree. This is indicated in the bottom status bar. Press the slash key to change the ordering. First 45 degrees, second axis aligned. Another slash key changes it to orthogonal mode, where only axis aligned lines are drawn. Return to the normal refraction mode by pressing slash again. It is possible to cycle through refraction options without leaving the line tool. Pressing the Shift key while moving the mouse temporarily overrides the current refraction. Now there is a crossing on the top layer. It could be worked around by a long detour, or with through-hole components we could just route the whole trace on the bottom side. But for the sake of the example, we're going to use vias to temporarily move over to the bottom side. First click the via tool, then place 2 vias along the rat line. Note, routing style sets via geometry. Now connect the 2 vias with lines on the top layer. Then CR to verify it's really just a short segment between the vias that's missing. Select the bottom ground layer and draw the missing line segment using the still active line tool. Now after a CR, all rat lines are gone. But remember, we have disabled rats for the ground net, but at least signal routing is done. To simplify the routes, it's best to turn off the visibility of the top silk layer by clicking its rectangle. Pressing the Del key while hovering over an object will remove that object. The object doesn't need to be selected. Now re-enable the rats for ground, or even better, enable all rats so nothing is left out of routing. Press CR for getting the remaining rat's nest for ground. It's best practice to have a solid ground polygon on one of the layers. Other tools often call this ground pour, fill or alike. In PCB-RND there are no special casings for this, it's just a polygon. Select the bottom ground layer and the rectangle tool. Using the 25mm grid and the visual feedback, click on the top left corner of the rectangular polygon to be drawn, then release the mouse button, move to the bottom right corner and click again. A large blue polygon has been drawn on the bottom side. Copper objects, other than terminals, are not associated to nets, so the new polygon is not a ground polygon, just a polygon. It has clearance to other copper objects by default, which means our 3 ground pins are still not connected. The easiest way to connect them is adding thermals on those 3 pins. This is done by selecting the bottom ground layer and the thermal tool. Clicking the pins will add thermal on the current layer. Pressing CR now shows all nets are connected. Shift-clicking the thermal tool will change the thermal, cycling through different styles. Removing the thermal is possible by clicking without shift, in which case the tool toggles the thermal for the given object on the given layer. Select the line tool and the outline layer to draw the centre line of the board outline. It is easiest to deal with the silk while copper layers are not visible. Turn them off. We have all subcircuits on the top side, so it is enough to edit the top silk layer. We're going to move refdes texts around, and we don't want to accidentally move our carefully placed subcircuits. The only floaters option is the inverse of lock floaters, and allows us to move floaters while other objects, subcircuits, lines, etc. are locked in place. The menu reveals that these 2 options are exclusive, so selecting one will automatically unselect the other. Clicking the selected one would unselect it, turning both of them off. Move the RefDes text out from under the subcircuits and use the Rotate tool to arrange them. It is a good idea to mark the positive and negative pins of the battery connector. The easiest way to do this is placing text objects on the silk layer. When clicking with the Text tool, a pop-up window asks for the text to be printed. It is also a good idea to print the name of the project on the board so the physical copies of the board are easier to identify later. For the sake of this example, the Line tool and the Rectangle tool can draw on the silk layer and, in fact, on any layer. Now the board is ready, don't forget to save it.